In section 3C, we will focus on the idea of continuous probability distributions. So it's important to note that in a continuous probability distribution, it's very similar to the discrete case in some ways, but it's different in other ways. So the idea of a probability distribution here has not changed. It's still basically we identify the possible x's and the corresponding probabilities, the same way as we do in the discrete case. However, in the continuous case, as you know, when we measure something, we theoretically have an infinite number of possible outcomes because we have this continuous variable, and between any 2 points is an infinite number of other possible outcomes. So we lose the ability to just list out those outcomes because there's an infinite number of them. So we can't list out the outcomes and assign probability to each outcomes. So what we do is we use the idea of a function. So a function, of course, is we use a continuous function to represent a continuous variable because now we can use our basically our x-axis to represent all the possible outcomes for x. So now we have this continuous scale that we can use to represent x. And then we essentially use the function or the curve to represent the probability. And technically, it is the area underneath the curve that represents the probability when we talk about a probability distribution. So there's lots of different kinds of probability distributions, continuous probability distributions, but we are going to focus on the normal distribution, which is essentially a bell-shaped curve. So you've probably seen a bell-shaped curve before. It's a very important distribution in statistics. It's very important as you move into the idea of inferential statistics. So we will really focus on the idea of the normal curve and how we find probability using the normal curve given a set of circumstances. So like I said, a normal curve is just a bell-shaped curve, which is a symmetric distribution. It is, of course, symmetric about the mean. And then, of course, the standard deviation will tell you how much variability you have in that distribution. So let's start with some examples. And it's important to note when you see this first example, you'll notice that it says the probability that z is less than 0.4. So it's important to notice that whenever we have a distribution, a probability distribution, we typically identify the outcomes as x. And that is almost always the case in statistics. When you have a probability distribution, the outcomes are x. There are a few exceptions to this, and this is one of them. Whenever we have what we call a standard normal distribution, we no longer use x, we use z. And the standard normal distribution is used so commonly in statistics that we really give it its own notation so that we know when we see a z value, we know that means standard normal distribution. So when you see a problem like this, it's very important that you notice that. You have to notice that this says the probability that z is less than 0.4. And the fact that it says z tells us, without it saying it in the problem, it tells us that we know this is a standard normal distribution. So what a standard normal distribution is it is a bell-shaped curve. But when we throw that word standard on there and we call it standard normal distribution, that means it is a bell-shaped curve with a mean of 0 and a standard deviation of 1. So it's very important you distinguish between whenever you hear normal distribution and standard normal distribution. Because a normal distribution is any bell-shaped curve with any mean and any positive standard deviation. However, a standard normal curve is just one of those many normal distributions. A standard normal curve or a standard normal distribution is specifically a bell-shaped curve with a mean of 0 and a standard deviation of 1. So that's what we're doing here. We're looking at what's the probability that we randomly select a value from a standard normal distribution, so a bell-shaped curve with mean of 0, standard deviation of 1. What's the probability that randomly selected value is less than 0.4? So with these kind of problems, what I highly recommend you do first, and what you should always do first, is just draw a picture of what you're trying to find. Because we will continue to build on this material and we will continue to draw these pictures, and it makes it much easier to see what you're trying to find. And some of these basic ones you could probably get by without drawing a picture, but it's a really good habit to get into. Just draw your picture every time you get one of these probabilities for a normal distribution. So if we draw our picture here, this is what it looks like. So your picture doesn't have to be perfect. It doesn't have to be a perfect bell. Some of mine look good and some of them look okay. Not all of them look great. That's not the goal. The goal is to just give yourself a feel for what you're trying to find. So just sketch out a bell-shaped curve, create that axis below it, and then always start by identifying the mean. And since this is a z distribution, it's a standard normal distribution, we know the mean here is 0. So you can see that line in the middle represents 0. So what we want in this case is we want probably that z is less than 0.4. So that's the next thing we should identify, is put 0.4 a little bit to the right of 0. Again, it doesn't have to be perfect, but 0.4 is obviously on that scale to the right of 0. The other thing that I like to do is I like to identify that these are z values. So I put the z there with the arrow. We have a z value of 0 being the mean, and we have this other z value of 0.4, which is really the value we're interested in here. And you'll see different things along that axis. That's why it's important to identify what it is, because in the whenever you do these kind of normal distributions, there's different things that will sometimes you'll want to identify along that axis, and you'll see some of those today. Once you do that, then it's nice to just shade in the region you're trying to find. So we have that value of 0.4 identified, so we want the area less than 0.4. So we shade in that area to the left, and we have a good picture for what we're trying to find here. We're trying to find that area to the left of 0.4. That's what probability is. Probability, proportion, percentages, they're all really the same quantity, but they're all represented in these curves, in these density curves, by the area to the left. By the area underneath the curve that we shade in, that we're interested in. That's how we identify probability in these cases. So once we identify our picture and we figured out what we want to find, then we will want to, in a case like this, we will want to use the table. So it's very important that you print off a copy of the standard normal distribution table. It is available through Blackboard, so make sure you print that off. You need that standard normal distribution table in order to find the probabilities, because mathematically finding the area underneath the normal curve is quite complicated, and it's something that we will not actually do mathematically, but what we will do is we will use a table in order to get that area underneath the curve. So I just cut off a little piece of the table. This is kind of the very top part of the table that you'll use to find these probabilities, and I'm not going to show you the table every time I do one of these problems, but that's where the probabilities come from, is they come from this table, and this is just the top part. So the table's kind of laid out in two different groups of z values. The first three columns represent all the negative z values, and then the last three columns in the table represent all the non-negative z values, basically 0 and all the positive z values. So the z-scores in the table are going to always be rounded to 1 decimal, so we're going to have to round to 1 decimal when we look things up in the table, and you'll notice I do that on all the problems. I'll round to 1 decimal. So we're getting a little bit of an estimate. We're going to get a little bit of error from the rounding, but that's not the goal. The goal is to really understand how this works and how to find the probability so that we can use this information later on in the course. So it's pretty straightforward to use the table. Basically, well, in those first three set of columns, you just look up the negative z-score if your z-score is negative. In this case, our z-score is positive. It's 0.4. So we actually look in those last three columns, and you'll see I just cut it off there at 0.4. So 0.4 is the bottom z-score over there on the right for those last three columns. So what the table always gives you is the table always gives you the area to the left, which is exactly what I want to find here. The table gives you the area less than a given z-score. So in this case, it's really simple. If we want the probability that z is less than 0.4, we just look up 0.4, and that will tell us the probability. It will give it to us both as a percentage and as a decimal. Of course, those are the same. So we will most commonly write it as a decimal, but you can switch back and forth between decimals and percentages. So you can see that we're going to write this probability to be 0.6554. And that's really how these work. We use what we know about the normal distribution along with the table, and we're able to calculate lots and lots of probabilities for these normal curves. Let's look at another example. So this one's a little bit different, but it's the same idea. The only difference in this one is now we're looking at, instead of looking at less than, we're looking at greater than or equal to. And by the way, the equal to does not really matter here. If you find the probability that z is greater than negative 1.9 or the z is greater than or equal to negative 1.9, that probability is the same because the area for a single point is always equal to 0. So that equality here really doesn't matter. So if you see greater than or if you see greater than or equal to, you treat those the same way whenever you go to calculate these probabilities. So first things first, always draw your picture. So this is what my picture looks like. Again, draw your curve, put 0 in the middle. Negative 1.9 is somewhere over there to the left of 0. We identify that as z. And in this case, we want the area greater than or equal to, so we want the area to the right of that. So we shade in that area to the right. So once we get our picture and we have a good feel for what we're trying to find, then we can go to our table. Now, this is where you really have to keep in mind that the table always gives you the area to the left. So if we look up negative 1.9 in the table, it's actually going to give us the area to the left of negative 1.9, and that is not what we want. We want the area greater than negative 1.9. But what we know is we always know that the total probability in any probability distribution is 1. We talked about this in the last section. So it's important you remember that the total area underneath the curve represents the total probability, and that total probability has to be equal to 1. So if we want the area to the left, if we want the area to the right, and we look up the area to the left, well, those two areas together have to be equal to 1. So we can just simply take 1 minus what we get whenever we look up this value of negative 1.9. And if you look up negative 1.9 in the table, you will get 0.0287. So if we subtract that, we will get the probability that we want. The probability that we want is 0.9713. So keep in mind, anytime you're finding the area to the right, essentially you always subtract whatever you look up from 1. That's basically the way it works. If you're finding the area to the left, you just look it up. If you're finding the area to the right, whatever you look up, you have to subtract it from 1 to get that area to the right. The third scenario that we'll sometimes deal with is sometimes we'll be interested in finding the area between two z values. So here we want the probability that z is between negative 2.3 and 0.6. So let's start with our picture. Your picture looks something like this. Draw your curve, put 0 on there. Here we put both of the z values on there. So we want to identify negative 2.3 and 0.6. And then we shade in that region, identify those, of course, as z values along that axis. So in this case, we actually have two z values to look up. And you have to really think about what the table is going to tell us. Remember, if we look these up, it's always going to give us the area to the left. So think about this. If you look up 0.6, it's going to give us the total area to the left of 0.6. And we want all of that area except for one small part. We do not want the part that's less than negative 2.3. So when we look up negative 2.3, it's actually going to give us the area that we don't want. It's going to give us that area in the tail to the left. So what we can do here, and this is what you always do when you are finding the area between two, is you look both of them up and then you basically subtract. Because we're going to take the area below 0.6 and then we're going to subtract out the area below negative 2.3, and that'll give us the area between those 2 points that we want. So if you look up 0.6, you'll get 0.7258 in the table. And if you look up negative 2.3, you'll get 0.0107. And this gives us the probability that we want, which is 0.7151. So these are kind of your three scenarios that you end up with, either the area to the left, the area to the right, or the area between two values. For the standard normal distribution, these are common kinds of questions, so it's important you're able to do these. So now let's move on to, well, what happens when we don't have a standard normal distribution, but we just have some normal distribution? So we don't have a mean of 0 and standard deviation of 1. So let's look at this scenario. Suppose a machine dispenses popcorn into 12-ounce packages. The weight follows a normal probability distribution. So when you read this question, it's very important you notice. It says we have a normal distribution. So that's key to knowing what to do here. We know we have a bell-shaped curve here. It also tells us the mean of this bell-shaped curve is 12 and the standard deviation of this bell-shaped curve is 0.6. So notice this is not a standard normal distribution. This is not a z. This is a normal distribution, bell-shaped curve. In this case, it's centered about 12, and the standard deviation is 0.6. So let's talk a little bit about the empirical rule. The empirical rule is a general rule that actually comes from the normal distribution. It basically just tells you how much of the data is within 1, 2, and 3 standard deviations of the mean. And the empirical rule simply says that within 1 standard deviation of the mean is 68% of your data, within 2 standard deviations is 95% of your data, and within 3 standard deviations is 99.7% of your data. So this is a common rule to estimate how much of your data is within 1, 2, and 3 standard deviations. It really comes from the normal distribution, but the percentages are always the same. It's 68%, 95%, and 99.7%. So let's draw a picture. Let me draw a picture so I can show you how you would lay out a picture for the empirical rule. A picture of this distribution might look like this. So you can see the bell-shaped curve. So always start with the middle, and you can see there in the middle is no longer 0 because this is not standard normal, but we are told that the mean of this distribution is 12. So I just write mu equals 12 there in the center of the distribution. So this bell-shaped curve is centered about the value of 12. We also know that the standard deviation is 0.6. So what you'll see I actually increment by the standard deviation. And you can see there across the top I have that line where it says sigma equals 0.6. So the distance between those lines I have drawn in that curve, the distance is a standard deviation. So this is something we commonly do in statistics. We commonly increment by standard deviation. We use standard deviation lots of times as our unit of measure because it gives us a consistent unit of measures across all different kinds of analysis. So standard deviation is an important descriptive measure, but it's also very important inferentially because we use it as a unit of measure a lot in the field of statistics. So you can see if you increase by 1 standard deviation, you get that value of 12.6. So that's nothing more than the mean of 12 plus 1 standard deviation of 0.6. If we go the other direction and we subtract 0.6, 12 minus 0.6 is 11.4. So that means between 11.4 and 12.6 is 68% of my data. And like I said, that 68% comes from the empirical rule. The empirical rule says that about 68% of your data will be within 1 standard deviation. So in this case, that would be 11.4 to 12.6. If we go out another standard deviation, you can see if we go to the left there, out another standard deviation, we just subtract another 0.6. Then we get 10.8. If we go to the right, we get 13.2. So that's 2 standard deviations below and above. So within that interval is 95% of your data. Again, that comes from the empirical rule. And then we can do the same thing with 3 standard deviations. You can see those farthest marks out there from 10.2 to 13.8. In this case, we would expect 99.7% of our data. So that's kind of the layout of any normal curve. And you can do this with any mean and any positive standard deviation. You just make the mean the center and you increment by standard deviation. This works for any normal distribution. All these pictures will look very similar. They'll have the same percentages. The only thing that will change is that X scale will change. So do notice that these are no longer Z's. This is just a random variable, normal random variable. So we call these X. We only call them Z if it's a standard normal. So these are X values. You can see that scale along the X-axis. So those would change. And of course your standard deviation would change. Everything else in this picture stays the same anytime you're representing the empirical rule. So part of the point of doing this is to show you that we can actually transform this x-axis. So we have this identified as x, but we can actually transform those x values into z values. And the way we do that, and I'll show you the transformation formula on a later slide, but the transformation formula is basically z equals x minus mu over sigma. And what a z-value means descriptively is a z-value tells you how many standard deviations an observation is above or below the mean. So if you use that z formula, x minus mu quantity divided by the standard deviation, then that will give you how many standard deviations a value is above or below the mean. So what we can actually do is we can actually use that formula and take all those x values along the x-axis, and we can transform them into z values. And if you do this, this is what you'll get. So for example, at the mean of 12, we get a z-value of 0. So if you take the observation x, which is 12, and you subtract the mean of 12, then you just get 0. Divide by standard deviation, it's still 0. So you always get 0 for the mean whenever you transform x into z. If we take that value of 12.6, we take 12.6 minus 12, that gives us 0.6. We divide that by 0.6, that gives us 1. That tells us that's 1 standard deviation above the mean. So you can see that z just represents 1 standard deviation. If we take 13.2 minus 12 is 1.2, divided by 0.6 gives us 2. That's 2 standard deviations above the mean. So notice we get 0, 1, 2, and 3 standard deviations above the mean to the right. And then we get, if we go to the left, we just get the same thing, but we get negative. So if you take 11.4 minus 12, then you get 0.6. I'm sorry, if you take 11.4 minus 12, you get negative 0.6. Divide that by 0.6, you get negative 1. So you're 1 standard deviation below the mean. So you get 1, 2, and 3 standard deviations below the mean there. So if you get a negative z-value, that means you're below the mean. A positive z-value means you're above the mean. An important thing to notice here is notice I did not change the shape of the distribution. I still have the same normal curve. But since all normal curves are the same shape, I can actually do this with any normal curve, and they all work out the same way. You end up with this same z-scale. I haven't changed the shape, and the shape of any normal distribution is the same. It's just a question of how you scale that axis. Here I have 2 different possibilities for how to scale it. I could scale it as x, or I could rescale it as z. Notice when I rescale it as z, notice what the mean of all those z values now are. The mean of x, if you look at the center, is 12, but if you look at z, the mean is 0. Look at the standard deviation. The standard deviation is identified as that distance between 12 and 12.6. It's that 0.6 for x. Well, if you look at that same distance for z, you can see that that distance is 1, which means the standard deviation for z is 1. So notice whenever I transform my x values into z, I now have a z distribution with a mean of 0 and a standard deviation of 1, which means it is a standard normal distribution. The reason why that is important is because now, if I have this in terms of z, then I can use my table and I can find probability. And because all normal distributions are the same, for example, if I want the area between 12 and 12.6, for x, that is the same as the area between 0 and 1 for z, because all normal distributions are the same shape. So this is what we use. We basically, if we have an x distribution that's normal, then we transform that scale into z, and then we can use our table in order to find the probability. Because we can't have a table for every possible normal distribution, as there's really an infinite number of those, because there can be any real number can be the mean. So you can't have a table for every normal distribution. But this one table allows us to calculate probability for any normal distribution through this transformation of x into z values. Okay, so let's do an example where we actually go through this process. So this is the same scenario, mean of 12, standard deviation of 0.6. We want to know what proportion of packages have a weight less than 11 ounces. So what we're essentially finding here, you can see the probability statement I have written out there. And you don't necessarily have to write these probability statements. Most people don't write the probability statements, they just draw the picture. And then the picture tells them what they need to find, and they just do the math from there. So you don't have to necessarily write the probability that x is less than 11. But that's what we're asked here. We're asked, what's the proportion of packages that have a weight less than 11? So we know this is not a z because it's not standard normal, so it's an x. So we say the probability that x is less than 11. So the next step, of course, is let's draw our picture. So we draw our picture here, draw your bell-shaped curve, put 12 in the middle because that's the mean, that's what we're told. And then we have a value of 11 over there to the right. So we identify that. Make sure you identify those as x. So we have these x values, 11 and 12. We want the area less than 11, so we shade that area less than 11. So the next step is to transform this into z, and I already have those written on the table, but you would do that next. I always write 0 for the mean for z because the mean is always 0 for z. But really what we need is we need the z value that corresponds to that x value of 11. And you can see I already have it written down there as negative 1.7. But here's how you get that value. To get the value for z, you can always use this formula. You use z equals, and I mentioned it before, but here it is written down, x minus mu over sigma. So to get that value, we simply take that 11 value for x, 11, we subtract the mean, which is 12, we divide by the standard deviation, which is 0.6. That will give you basically negative 1 2/3. So we are going to have to round this in order to use the table. Like I mentioned before, the table is only accurate to 1 decimal. So I just say that's approximately negative 1.7. So that's where that z of negative 1.7 comes from. So notice when you're finding probability for x, what you do first is you draw the picture in terms of x. Then you rescale those using this formula. You rescale those into z values. And we rewrite below the x, we rewrite that this as a z, this value of 11 is now negative 1.7. So mathematically, and you don't necessarily have to write this probability statement out, but mathematically what that means is that the probability that x is less than 11 is equivalent to the probability that z is less than negative 1.7. So once we are at this point, then it's really straightforward. It's exactly what we had done before. So you kind of have one additional step here, which is the first step is to transform x into z, and then once you transform it into z, you're doing exactly what we did before with the table. So to find the probability here, you just look up negative 1.7 in the table, and of course that will give you your probability. If you look that up, it is 0.0446, so that's how those work. This one here is similar, but we're finding a different area. I'm still using the same x value, but here I say, what is the probability a randomly selected package has a weight greater than 11 ounces? So if we write out our statement, that's just probably that x is greater than 11. So you can see our picture here is almost the exact same picture. The only difference in this picture, of course, is the area that we shade, because in this case, we're interested in greater than 11 ounces. But other than that, it looks exactly the same. So here we've already calculated the z value. We figured that out on the last question. We figured it out to be negative 1.7, so that's exactly the same process. So I'm not going to do it again. I just want to make sure that we're good with this means that the probability that z is greater than negative 1.7. So I just want to make sure that you're aware of when we find the area to the left, like the last one, we just look it up. When we find the area to the right, like this one, we have to subtract that from 1. So this is actually the complement of what we did in the last question. So we just take 1 minus 0.0446, and that will give us the area to the right that we want. That will give us 0.9554. So all these work very similar to what we did with the z distribution. Of course, the big difference is you have that additional step of transforming x into z. Let's just do one that is in between. What is the proportion of packages with a weight between 11 and 12 ounces? So if we write out our probability statement, we're finding probably that x is between 11 and 12. So again, the picture is exactly the same picture other than the area that we're shading. So here we're shading the area just between 11 and 12. The z transformation is the same. We know the z for the mean is always 0, and we already calculated the z for 11 to be negative 1.7. So if we rewrite this in terms of z, that means this is mathematically equivalent to the probability that z is between negative 1.7 and 0. So when we find the area between two values, we look them both up. The area less than 0 is always 0.5, and you can look that up in the table, but honestly, you should probably be able to figure that out because we know the total area underneath the curve is 1, so that means half the area is to the left and right of the mean. So if the total area is 1, that means the area to the left of the mean is 0.5, so you get 0.5 for the area less than 0. If you don't recognize that, you can always look it up as well. If you look up negative 1.7, you will get that 0.0446. We subtract those. That'll give us the area in between. That'll give us 0.4554. So remember, anytime you're finding the area between two values, make sure you look them both up and you subtract. Okay, let's look at one more example. So here we're going to look at the life of a certain type of motor is normally distributed with a mean of 10 years and a standard deviation of 2. So the first question says, what is the probability a motor will have a life less than 14.5 years? So our probability statement looks like this. We're going to say the probability that x This is not standard normal. It's got a mean of 10, standard deviation of 2. So we want the probability that x is less than 14.5. Draw your picture. So draw your normal curve. The mean is now 10. So that means we put that center line there at x equals 10. And then we're interested in a value of 14.5. So that's somewhere over there to the right of 10. We're going to next transform those into z's. Well, once we identify those values, we want the area to the left. So we shade the area to the left of 14.5. And then once we get our picture set up, then we're going to write out those z values. So the z value for the mean, as we've said, is always 0. The z value for 2.3, I already have it written on the graph, but that is what you have to calculate. So here's where we use that formula, x minus mu over sigma. We take that x value of 14.5, subtract the mean of 10, divide by 2, we get 2.25. We will have to round that again. It's a little bit. You'll get a little bit of rounding error here, but very little. So we do have to round that to 2.3. So just use your typical rounding rules in order to round those to 1 decimal so you can use the table. So now that we know that the corresponding z value to this x is 2.3, we can rewrite this probability statement as the probability that z is less than 2.3. And like I said before, you don't necessarily have to write these probability statements. If you want to just create the picture, then you can just know I'm finding the area to the left of 2.3, and you can just look up 2.3, and that'll tell you the answer. You don't necessarily have to write these probability statements like I do. The main thing is you understand the process. If you look up 2.3 in the table, you'll get 0.9893. So of course that is the probability. All we have to do is look this one up because we're finding the area to the left. And when you're finding the area to the left, that is what the table gives you. What if we want to find this one? What proportion of motors will have a life greater than 12.5 years? So your probability statement is we randomly select a motor. What's the probability its life is greater than 12.5? The probability that x is greater than 12.5. Your picture. So 10, of course, is the middle again. 12.5 is over there to the right somewhere. Here we want greater than, so we shade that area to the right. We identify those. Those are of course, our x values. Then we want to transform those into z. So the z for the mean is always 0. We have to figure out the z for 12.5. Here's the math for that. 12.5 minus 10 is 2.5 divided by 2 gives you 1.25. So we will round that to 1.3 to look it up in the table. So in terms of the probability, we can rewrite this probability statement in terms of z. So we can rewrite this as the probability z is greater than 1.3. Those are mathematically equivalent. Since we're finding greater than, in this case, we're going to have to look up 1.3, subtract it from 1. So we take 1 minus, we look this up, we get 0.9032. So we do our subtraction here, and we will get 0.0968 as our probability. Let's do one in between. What is the probability a motor will have a life between 7 years and 9 years? So your probability statement is going to look something like this. The probability that x is between 7 and 9. So draw your picture. Normal curve, symmetric about 10. That's the mean. Here we have two x values, which are 7 and 9. So we need to identify both of those along that x-axis. Identify those as x's. And then, of course, we want the area in between those. So we need to shade that area. Then the next step, transform those into z. So I already have them written down there, but the mathematics of it goes like this. We basically plug in 7 for x, and we get a z value of negative 1.5. Plug in 9 for x, you'll get a z value of negative 0.5. Now we can rewrite our probability statement. Now that we have those z's, so we can rewrite this as probability that z is between negative 1.5 and negative 0.5. We're finding the area between two values here, so we have to look them both up and subtract. If you look up negative 0.5, you'll get 0.3085. If you look up negative 1.5, you'll get 0.0668. Subtract those. That gives us the probability we're trying to find, which is 0.2417. One more type of problem. So this is the last thing that we will look at. And this is one that I don't ask very often, but you should be able to do a problem like this. Every once in a while, you'll see a problem where instead of finding the area underneath the curve or finding the probability, instead you'll be given the probability or the area under the curve, and you will be asked to find the x value that corresponds to that area. So it could be something like this. Suppose the manufacturer is willing to replace 3% of motors that fail. How long a guarantee should they offer? So they're basically willing to replace the first 3% of motors that fail. So that means the 3% of motors that have the shortest life are the ones that they would be willing to replace. So we need to figure out at what x value at what point, at what x value will we be able to identify that will allow us to replace 3% of the motors. So the key here, honestly, is the picture. If you draw a good picture, it's not that hard to solve these, but you've got to draw a good picture. So when you draw your picture here, you start with the normal curve like always, and then, of course, you identify the mean in the center, which is 10 here. But the thing that's different here is now we have to shade the area based on the percentage that we're given. So we're given the lowest 3% is what we're willing to replace. So that means we need to shade the area to the left. That's going to be the lowest 3%. And we need to shade that area, and we need to identify that. That's 3% or 0.03. So then on the axis there, we can just identify x, because that's really what I'm trying to find. I'm trying to find that x value that corresponds to that bottom 3%. And I go ahead and just put the x out there like I always do, just to be consistent. I put the x in the arrow, but really that x value there underneath that point where we identify 3% below that point, that's really the x value that I need to find. I need to find that x value. So in order to find x, you kind of do the same thing. You still need to get z in order to do that. We know that the z for the mean is 0, but how do we get that z of negative 1.9? So you cannot use the formula to do this because you don't know x. Instead, you know the percent. So here's where you have to actually use the table, but you use the table backward, because the table always gives you two things. It gives you the z, and then it gives you the corresponding probability or percentage. So normally we use the table and we look up z and we find the area. But we can also do it backward. We can look up the area and find the z, which is what you have to do in these kinds of scenarios where you're given the area. So what you have to do is you look in the table and you just look at the percentages and you find 3%. So you're probably not going to find 3% exactly, so you're going to have to pick the closest one. This goes back to the idea of we only go to one decimal point on the z values, so you are going to be limited a little bit in terms of accuracy. But you can see the closest percent in the table is 2.87%. So that's almost 3%. 2.87%. If you look up negative 1.9 on the table, you'll see 2.87%. So that's about 3%. That's as close as we can get, which means our z value here is negative 1.9. So that z value you have to get from the table. And then once you get the z value, it's not hard. You do want to use this formula. This is nothing more than just the z formula already solved for x. But I recommend that you have this formula to use rather than have to use the z formula and then solve for x. This is just the z formula already solved for x. So we know everything in this formula except for x. So we know the mean. We know the mean is 10. We know the standard deviation is 2. And we just said that z is negative 1.9. This is 1.9 standard deviations below the mean. So if we just plug that in, 10 plus 2 times negative 1.9, that'll tell us how long we can provide a warranty for these motors and replace 3% of the motors. So that's the last kind of problem. We don't do a lot of those, but every once in a while we'll have you find an x value based on a percentage. So the big things in here is just understanding what a normal distribution is, a standard normal distribution, understanding some of the characteristics, and then of course being able to find the probability for the standard normal, the probability for the normal, understand what the empirical rule is, and be able to do these last kind of problems where you're given a percent and you're actually finding an x value rather than the probability. That's what we focus on in this section. That is the end of section 3C.